Okay. So, it's a big, scary word. It's not really a big, scary topic, bless you. Some people think that it's going to be until they start doing it. So why do we need to learn about it? No. It is. It's all dealing about lab. We can do lab accurately if we can do stoichiometry. So, we can do things like determine the amount of reactants needed for a reaction. And this is what we do in industry. So a subdivision at 3M is making a film that is used in in TVs, film that goes inside the TV screen. Well, they don't actually make and manufacture the TVs, but they make and manufacture the film that the TV manufacturers like Sanyo end up buying. Well, 3M's not going to just randomly say, okay, we'll put this stuff together and see how much we get. That wouldn't be very effective. Or say, well, I need 100 tons of this, so I'm going to take 100 and 100 of my two reactants and put them together, and I should get at least 100 tons out. They're not going to do that. They're going to systematically say, well, my TV company needs me to have 10,000 yards of film. And I can go back through my reaction to figure out how much of the reactants I need to purchase as 3M so that I'm not buying more than I need to. Because that cost would then go to the TV manufacturers, which would then go to you guys buying the TVs. And if it's too expensive, you're not going to buy it. So they need to be very particular on that. You can also predict the amount of product that would be obtained. And we're going to just get more and more accurate as we do our labs. So, first non-example, baking chocolate chip cookies. If you know that you want to have enough cookies for the people in the class, but you don't want a whole lot of leftovers because you don't want them all at home, because you don't want to eat all of those extra cookies, you figure out how many you need, and then you can go back to figure out how much of the ingredients or the reactants that you need to make the amount that you want. That way you're not being wasteful. So here are our keys to stoichiometry. These are the big important things. First of all, we need to make sure to balance the equation. This is one of the key things that people end up forgetting. It's going to be detrimental if you do forget it. So that's why we have that as our first thing, to balance that equation first. Then we do some organization. So we read through the problem, figure out what is actually given to us and what we actually need to get out of it. Some of it might be extra information that you don't need to worry about, just like math problems, and when you're doing reading tests, sometimes there's extra information that you don't actually need to know about, that you can ignore and still do the problem correctly. If we take this step to actually organize it, we're going to make sure that we only use the information that's necessary. We're going to determine any molar or molecular masses that are needed. And the units for those, we've done this before, gram per mole, and we add it up by looking at the periodic table. So we've done balancing before, we've done organizing in our life before, we've figured out these molar masses before, and we've done some of these conversions before as well. So you're going to set up conversions where you have the given thing is always first, and then we set up fractions with ratios of things. So I would have a ratio that has the same unit as my given on the bottom so that I can cancel it out. So the thing I want to get rid of, or the unit I want to get rid of, goes on the bottom. And whatever I want, whatever unit I want to get to, goes on the top. It's unlocked, so if they need to get in, they can. The maximum that you will need are 3 fractions. Hi. Thank you. Thank you, thank you. Thank you, Mohammed. Thank you. Perfect. Oh, wow. Thank you. If you want to set them up there, that would be good. Thank you. That way they won't tumble. Thank you. Okay. Again, the maximum that you're going to need for any of these is 3. So you've done dimensional analysis in AP Environmental Science if you took that, or in Science 9 2 years ago, depending on who you had at what time. You've done this. And sometimes you've had really long ones. The maximum you're going to get is 3 here. Easy. Easy peasy. But the key to remember is that you need this step. Anytime we want to go from one element or compound to another element or compound, we need to use moles. If we don't use moles, we can't get to the new thing. And the coefficients from this balanced equation are the number of moles. If you can remember that, it's going to be easy for you. So let's take a look. Let's figure out first problem here. We've got tin 2 fluoride being made from 55.0 grams of hydrofluoric acid with more than enough tin. So this is some of that extra information. When it says more than enough, that means it is in excess. It's a definition we're going to hear more of later today. But it's in excess. So the first step is always to balance it. How do we get this one balanced? Got it, Alexis? Yeah, 2 in front of the hydrofluoric acid or hydrogen fluoride. Excellent, thank you. And now I'm balanced. So my first step is done. One of my most important steps, done. We're good. Now we can identify what we have. So the excess information, I don't have to write that down. I do want to write down my given though, because that's where I'm always going to start. 55.0 grams of HF. And I want the mass, which is going to be in grams, of tin 2 fluoride, SnF2. This is going to be our longest one. This is one of the 3 steps. Whenever I go grams to grams, I'm going to have whatever my given is, and then 3 fractions. So this is the longest type you'll ever see. That's why we're getting it out of the way right away. So if I'm doing mass to mass, I need to know the molar mass of both the thing that I'm starting with and the thing that I'm ending with. So I need the molar mass of HF. So I look at my periodic table. Fluorine's 19. Hydrogen is 1.01. We rounded just about to 20. Just keep working. I can come over later. Just keep working on the rest of it. Okay. So that's 20 grams of HF for every 1 mole of HF. Yep. Yeah, so the mass of fluorine is 19, the mass of hydrogen is 1, so I add 1 and 19 and get 20. Good question. I have to do the same thing with my tin 2 fluoride, so I need the molar mass of SnF2. Look at your periodic table. When somebody has it, let me know. Sounds good. 236. Sounds good. Did anybody else get that? One tin plus 2 fluorines. I'm gonna double check before we continue. Yep. Plus 1 of the tins, yep. 156, okay. Okay. So we'll round up 157. Thank you. Okay. So I always start out with my given, which I identified up here, as 55.0 grams of HF. I know I don't want HF at the end, so I know I need to get to moles of HF. So my first fraction is going to be based off the molar mass that I determined here. The thing I want to get rid of is grams. So 20 grams of HF goes on the bottom. 1 mole of HF is the other part of this ratio. It's always going to be 1 mole with whatever my mass is. It's going to go on top. And I set up my next fraction. And for this one, I need to look at my balanced equation because I'm going from one compound to another. Anytime I go from one compound to another, I look at my balanced equation. So I need to know moles of HF, that's the one I'm getting rid of, and moles of tin 2 fluoride, that's the one I want to get to. The one I want will go on top, so 1 mole of SnF2 goes on top, and on the bottom goes 2 moles of HF. Oops. We're going to have 1 more to set up. Because I'm at moles of tin 2 fluoride, I'm not to mass yet. I need my unit to be grams. So I look at my other molar mass that I figured out. This time, 1 mole is going to go on the bottom. 1 mole of SnF2 goes on the bottom. And the mass, 157 grams of SnF2, goes on top. Everything across the top gets multiplied, and then everything on the bottom gets divided by that. Go ahead, type it in. So 55 times 157 divided by 40. Yep, because 2 times 20 would be 40. And we'll need 3 sig figs. 215? Okay, so 216. Cool. 216 grams of SnF2. And let's do a double check, make sure my units are canceling out correctly. So I have a grams of HF on top. I also have a grams of HF on the bottom. So my units, grams of HF, cancel out. I have moles of HF on the top. I also have moles of HF on the bottom, so those cancel out. Moles of tin 2 fluoride cancels out with a moles of tin 2 fluoride that's on the bottom. My last unit that's left is grams of tin 2 fluoride, so I set it up correctly. What questions do you have so far? Okay. We are going to skip example 2. Okay, we are dealing with limiting reactants. So this is our main application of stoichiometry. This is why we get to do a s'more lab tomorrow. Yes. Woo-hoo. So here's 2 definitions for you. First one, excess reactant. We already picked out the excess reactant in the last problem. So we've seen the application there. It's the reactant that will not be completely used up in the reaction. There's going to be excess of it in the beaker, in the reaction beaker at the end. It's going to be leftover stuff at the end. The limiting reactant is the reactant that is completely converted in the reaction. The reason we call it limiting is because it limits the amount of product we can get. Hopefully you ate a lot at lunch because I'm going to use another food example. Save a little bit of room tomorrow for the s'more. But today, hopefully you ate plenty. Okay, so here's our non-chemistry example. We can buy a pack of hot dog buns that have 8 hot dog buns in them. And we can buy a pack of hot dogs that have 10 hot dogs in them. And there's enough ketchup in the bottle for 40 hot dogs. What's going to be in excess? So what's not going to be used up in making hot dogs, which are going to require 1 hot dog, 1 bun, and 1 serving of ketchup? Ketchup, yeah, there's going to be a lot of ketchup left over. Is there going to be anything else in excess? Something not used up? Yeah, the hot dogs. There's going to be 2 extra hot dogs left over. So, which one is limiting? The buns. Yeah, the buns are limiting the amount of product I can get. What's the maximum amount of hot dogs that we could theoretically make and eat? 8, yeah. Because of the amount of buns. So we'll write it down. Excess, ketchup, and hot dogs. Limiting, buns, max we can make is 8. This is called our theoretical yield. I'm going to be looking for that a lot in labs. So our maximum here that we could make, theoretically, assuming everything goes as planned, like I don't burn one of the hot dogs really bad by letting it fall into the fire, theoretically, assuming all goes well, I could have 8 good hot dogs. Assuming a bird doesn't swoop in and pick up one of the buns. If you can understand this concept, you've got limiting reactants down. Yeah, in a good way. If you can get this, there's this thing that we see in Gen Chem classes is people don't get this concept. If you can grab this concept and understand that, well, the one that limits the amount I can get are the buns, you're going to be fine. throughout this unit and on the test next Tuesday. But let's put it to some actual calculations. So we follow the same procedure that we're doing for stoichiometry. Sometimes 1 step, sometimes 2 step, maximum 3 step. And we just need to make sure to know and compare the amount of products that we can get out. So, here's our limiting example. It says if we react 2 moles of HCl with 3 moles of calcium carbonate, which is the limiting reactant? I have 2 givens here, which is good because I have 2 reactants. I need to check each of my reactants to see how much of the products I get. First step, always balancing. What number goes in front of the HCl? 2, yes. So 2HCl plus CaCO3 goes to CO2 plus H2O plus CaCl2. No, I'm already tongue-tied. Okay, you get to pick any of these products because it's not telling us specifically that it wants one. It's not saying determine the theoretical yield. It's not saying figure out how much water you could get out. So you get to pick. You can pick any of these products as long as you stay consistently with that product. And I'm going to pick calcium chloride just because that's what I picked when I did the PowerPoint. And so I'm picking it again. Okay, so I'm picking one. You just have to pick any of the products unless it tells you something specifically. It's not telling me specifically, so I pick CaCl2. So I have to figure out what I have and what I want. I am given, for my first conversion, 2 moles of HCl. And I want the one that I picked, which is the moles of CaCl2. Do I have mass in either the HCl or the CaCl2? No. So, lucky for us, we have moles, we want moles, we can ignore mass altogether. I don't need to look at the periodic table for this one. It's going to just be a 1-step mole-mole ratio. So I start out with my given, 2 moles of HCl. I'll write that out first. 2 moles of HCl. And I set up my 1 fraction that I need for this one. I'm going to have to look back at my balanced reaction because that's where the numbers are going to come from. So I'm looking to get moles of CaCl2, and I'm looking to get rid of moles of HCl. Moles of HCl goes on the bottom because I'm trying to get rid of it. Well, what number should I put with my moles of HCl? 2. Why? The moles of HCl will cancel out. Yes. Where did you get that 2 from? Yeah, it's from the balanced equation, exactly what I was looking for. So that 2 comes from the balanced equation. So if that came from the balanced equation, what number do I need to put with the CaCl2? 1, yeah. If you look at the coefficient in front of CaCl2, it's 1. So I would take 2 multiplied by 1 divided by 2. I will get 1 mole of CaCl2 when I react 2 moles of HCl. So there's the first part of my answer. But I have another given. If I have another given, I have to do another equation. So our second conversion is with my second given, 3 moles of calcium carbonate. And again, I'm looking for moles of calcium chloride. And again, we have moles. We want moles. We can ignore mass altogether, so we're going to have another 1 step. Start out with my given again. And this time, if I look at my coefficients, I have 1 mole of CaCl2 for every 1 mole of calcium carbonate. 3 times 1 divided by 1 is 3. So this is saying when I have 3 moles of calcium carbonate in the lab and I want to react, I will theoretically get 3 moles of calcium chloride out. Have I answered my original question? No, I have not. My original question is, which one is limiting? Well, I have all of the information that I need now. I just need to take that last final step of analyzing it. I'm going to wait a few more seconds for a few more pens to stop. So, the HCl gave us 1 mole of calcium chloride. The CaCO3 gave us 3 moles of calcium chloride. What is the maximum amount of calcium chloride I can get from this reaction? 1. Yeah. The maximum I can get by reacting these initial stuff is 1 mole of calcium chloride. So, the HCl is limiting because it limits the amount of calcium chloride I can get. The calcium carbonate is in excess. There's extra of it. If I had more HCl, I could make more because my calcium carbonate would let me allow me to do that. What questions are there now?